finally see, and the Church Farb Putman conjecture.
Yeah, thank you. Thank you for the opportunity to speak. It's awesome. Right, so as advertised, I guess the main goal of the talk is to introduce the Steinberg module. I guess in an effort to coordinate with Jeremy for his talks, I'll be setting us up for his talks tomorrow by saying a little bit about what the Steinberg module is. And I guess specifically talking about its connection to the Church Farb Putman conjecture. Great. Okay. So the setup is we will start with V, a finite dimensional vector space over a field F. Okay. And I will use the notation T of V to mean the Teats building associated to V. So this is a simplicial complex. This is the simple simplicial complex that is the geometric realization of the poset of proper non-zero subspaces of V as ordered by inclusion. So concretely, that is to say that this is a simplicial complex where the vertices are in correspondence with subspaces of V that are non-zero and proper. Okay, and the p-simplices of this complex correspond to flags. To flags of these subspaces. Great. So there is a nice action of GLV on the Teats building. GLV acts on V, so it in such a way that it acts nicely on subspaces, and so there's an induced simplicial action on the Teats building. Okay, very basic examples. So when n is 2, and we consider a two-dimensional subspace, then the Teats building is just going to be a discrete set.
Wrote n instead of 2.
I wrote n instead of 2, thank you. Discrete set of lines in F2. Okay. When n is 3, then we get a bipartite graph. Okay, so on one hand, I have vertices corresponding to all of the lines in F3. On the other hand, I have vertices corresponding to all of the planes. And then the edges correspond to containment. Okay. And if my field is infinite, then this graph, this complex, is going to be locally infinite once n is at least, once the dimension of V is at least 3. Okay. So it's a theorem of Solomon and Tits that the homotopy type of the Teats building is a wedge of spheres of dimension n minus 2, dimension of V minus 2. For an infinite field, there will be infinitely many spheres in this wedge. Okay. And So now we can define the Steinberg module by definition. It is the single non-vanishing reduced homology group of this wedge of spheres. Great. And we'll view it as a GLV module. Oh, and actually, to make my life a little bit easier, I'm going to just define it to be a rational vector space today. Great. Okay. So, one reason to care about the Steinberg module, maybe the first reason I cared about the Steinberg module, is Borel-Serre duality. So, if we consider, I guess now we'll specialize to the case where we're looking at vector spaces over the rational numbers, and correspondingly, I'm going to consider the group SLNZ. Great. So rationally, this is not a Poincare duality group. Does not satisfy Poincare duality. However, Borel-Serre duality says that it does satisfy maybe the next best thing, which is the following. So they proved, well, first of all, they proved that this group has a finite virtual cohomological dimension. So the VCD of this group is equal to n choose 2. Great. So the definition, by definition, of VCD is the common cohomological dimension of all the finite index torsion-free subgroups of SL and Z. But relevantly, this number gives an upper bound on the degrees where we can have non-zero rational homology. Okay? And they proved, by studying the Borel-Serre bordeification of the symmetric space associated to SL and Z, and using the appropriate form of Poincare duality, they proved that we have the following duality statement, that the codimension I cohomology of SL and Z is naturally isomorphic to the dimension I homology of SL and Z, but with twisted coefficients in the Steinberg module for Qn.
So you can replace the trivial representation by any one, right?
Oh yeah, absolutely, that's right. So if you want to study cohomology with coefficients in your favorite SL and Z representation, so replace this with M, then the same equation holds, but we would have to tensor M over Z with the Steinberg module. Yeah, perfect. Okay, great. So here's the picture of what we have. Here's N and Q. I'm looking at the degree Q cohomology of SL and Z with trivial rational coefficients. And great, on one hand, we have this quadratic in N, VCD, and we have vanishing above that number for formal reasons. And on the other hand, as Oscar mentioned in his talk, classical results by Borel show that we have this range where there's homological stability. Which is to say that when n is large relative to q, then up to isomorphism for fixed q, the isomorphism type of these homology groups stabilizes. Okay. Great. So, right, if SLNZ were a Poincare duality group, then homological stability in this region here would imply a sort of dual notion of stability up by the VCD. And Church Farb Putman conjectured that even though they're not a Poincare duality group, that we still have the sort of dual stability that you would expect if they were. So Church Farb Putman conjectured that if you look at the codimension I cohomology of this group, trivial coefficients, that these groups are going to stabilize, they're going to be independent of I eventually. And in fact, they explained, Church Farb Putman explained, that if we do have this stability, we would in fact expect the stable groups to be 0. So this is for all n greater than or equal to I plus 2. Okay. So in terms of our graph, what this says is that we have this dual range here where conjecturally there's range. Okay. And their conjecture is that the height of this region is growing linearly in n. Yeah.
So Stn of Qn, is that the same as Steinberg of Qn, or does the sub n mean something else?
No, the n1n is superfluent.
On the bottom board on the upper right?
You have Steinberg n of Qn.
Oh, I'm sorry, yeah.
Yeah.
I made the horrible
Okay.
decision to use the notation in this talk that is not my usual notation. And I just can't do it. It was, yeah, usually I write Stn of Q.
Okay, so Stn of Q is the same as St of Qn?
It is,
Okay.
yes. Thank you for the question. I will make that mistake 12 additional times in the talk. So I'm
Okay.
in charge of correcting me. Thank you. Great, okay, so, great. Conjecture, dual stability, stable groups are 0. And here is some current progress on this conjecture. Oh my gosh, that was not the texture I was expecting. Paper.
The big sponge is, I think, the most pleasant one.
Camouflaged. It just runs over the desk. Ah, that's more efficient. Okay. So, progress to date. This conjecture holds when we consider codimensions 0, 1, and 2. So, great. So the conjecture holds for I equals 0, 1, and 2, and all values of n in the stated range. More specifically, in the 70s, Lee and Sharba proved that there is vanishing in the top degree okay. And then it follows, I guess it follows from work of Baikovsky from the early 2000s, and then was proved by Church Farb in, Church Putman in the 2010s, And then just last month, there's a much simpler proof that's in the paper by Charlton, Radchenko, and Rudenko, which proves the codimension 1 case of the conjecture. So we have vanishing of these groups once n is at least 3. And then a couple of years ago, in joint work with Brook, Miller, Pat, Stroka, and myself, we showed the codimension 2 case for all n at least 4, and in fact, it happened to hold for all n at least 3. Okay, great. And so this is some progress to date on the conjecture. And I think we'll hear maybe throughout the week some other perspectives on this conjecture. For example, the connection to the Rognus conjecture that Jeremy will talk about. But I'll focus on the approach to this conjecture that was taken by Lee Sharba and Church Putman and our paper, which is the following. So, right, here's an observation that one way that we can approach this is that, well, in light of this Borel-Serre duality theorem, these codimension I cohomology groups are identified with these degree I homology groups with coefficients in the Steinberg module. So, right, one approach to studying these groups is to study flat resolutions of the Steinberg module. Right? So one approach is we can take a resolution of the Steinberg module by flat SLNZ modules. Take covariance. And then take homology. And those homology groups are exactly the groups in question, these codimension I cohomology groups. Okay. And so the game becomes the game of trying to come up with a flat resolution of this Steinberg module where the terms are somehow small enough that we're able to get some traction in calculating these coinvariants. Okay? Okay, so the goal is to find a resolution that's small enough to compute coinvariants. And ideally one where the coinvariants just vanish. Okay. Great. So let's review the structure of these Steinberg modules. So, the definition. To start with, I'm going to fix a frame, L1 through Ln of q to the n. So by a frame, I mean I'm going to fix a direct sum decomposition into n lines. Okay. And associated to this frame, we have a subcomplex of the Tietz building, defined as follows. So this is called an apartment. I guess for those who study the kind of the combinatorial theory of buildings, by definition, a building is a union of a collection of distinguished subcomplexes called apartments. And in the case of SLNZ, the apartments are defined to be the full subcomplex spanned by all vertices of the Tietz building that correspond to direct sums of these lines. Excellent. And so for every choice of frame, I have this corresponding subcomplex. And so really concretely, when n equals 2, then this subcomplex, well, it's just a zero sphere, a pair of points. When n equals 3, it's a circle. I have 3, L1, L2, L3 plus L2, L1 plus L2, L1 plus L3. Okay. And in general, it's not hard to check that these are these subcomplexes simplicity are going to be simplicity isomorphic to the barycentric subdivision of the boundary of an n-1 simplex. So, right, topologically they're spheres. These are the Coxeter complexes of type A. Okay. Great. So, importantly, each of these spheres, the inclusion of each of these spheres, well, if I consider the image of its fundamental class, then these give us homology. So this associated homology group is called, I'll call it an apartment class. And if I fix an order on my lines, then that will determine an orientation on the sphere, and so signs will be well defined. Okay. Great. And right, in this notation, the action of SLNZ is just like acting diagonally on the right on these lines. So, right, it follows from the Solomon-Titz theorem that the Steinberg module is generated by these apartment classes. Okay. Though, unfortunately, it's not totally immediate to compute the covariance for the following reason. So, right, observe that if you were acting by SLN Q, the action on the set of frames would be transitive, but SLNZ does not. Okay, and be really explicit about that. Be really explicit. I'll use the convention that when I'm writing down one of these symbols, one of these apartment classes, that I will write the lines by choosing a generator for the integer points. So that's, I guess, canonically defined, I guess, up to multiplication by a unit, by plus minus 1. Okay, so okay, and so with that convention, we can see that, for example, these two classes are going to be in different orbits of the action by SLNZ, since this one's determinant 1 and this one's determinant 2, for example. Okay? So I'll just say the frames are in different SL2 Z orbits. Okay. But it's a theorem of Asch and Rudolph that, okay, right, so we said the Steinberg module is generated by apartment classes. The apartment classes are not a basis. And in fact, the Steinberg module is generated by integral classes. It's generated by the, in this notation, the matrices of determinant 1. So these are our integral apartment classes. Okay. And moreover, Bykovsky proved a presentation for the Steinberg module. So it's a theorem Bykovsky that the Steinberg module, oh, I did it again. The Steinberg module is the following. Well, if I take, first of all, the freewheeling group on all my integral apartment classes, we're working rationally. Steinberg module is rational today. Okay, so we take the vector space on all the integral apartment classes, and Bykovsky proved that the Steinberg module is isomorphic, or is, the quotient via the following relations. So the first relation is that if I apply a permutation to the lines, then that will change the class up to sign. This is quite straightforward to check. This is just the statement that if you permute these lines, you can check what that does to the orientation of the sphere that is the associated apartment. That's not hard to check. Okay. And then the next relation is the following. So to write this down, I'm going to choose integer, yes, I'm going to choose integer generators for each of my lines. Okay, so primitive integer vectors. And the relation says that I have equality between this symbol and the following. So here's the picture here. At least in the n=3 case. Again, here I'll go by V3, V1. V2, these dots in between are the planes spanned by a pair of those lines. And you can check that I can subdivide this apartment into the following two apartments. Okay? And so correspondingly, we get this relation. And here it was important that I took this linear combination of V1 and V2 with unit coefficients, so that these would both give me valid apartments. Great. Okay. Good. And so, right, given this theorem by Bajkowski, checking the statement of the Church Farb Putman conjecture in codimension 1 follows very easily. And so let me go over that. Actually, I'll go over the codimension 0 case. So, right, I'll say the CFP conjecture in codimension 1 follows from this presentation. Okay, and let's look at the proof in codimension 0. So this is the result originally due to Lee and Sharba, but I'll give an anachronistic proof by using this result of Ash-Rudolph that gives the fact that the Steinberg module is generated by these integral apartment classes. Okay, so here's the proof. So using the theorem of Ash-Rudolph of generation by integral apartment classes. Okay.
Jenny?
Yeah.
Before you go down there,
Please, yeah.
the example of the subdivision. Shouldn't I have some thing with V1 plus V2 a vertex of?
Shouldn't I have, sorry?
I mean, in this equation, you have the V1 plus V2 should be a vertex of these two sub-apartments on the right, right?
V1 plus V2.
I mean, V1 plus V2 appears as an entry in these lists on the bottom of the board there, right?
Yes.
Yeah, so shouldn't it be a vertex
Here.
But shouldn't there be an edge between that vertex and?
So this is this. Let me throw in.
Sorry.
No. I'm hoping this part will be understandable. So let's make it more explicit.
There's a homologous.
Just V1, V3. Oh, that one's around.
There's a homologous picture where you have two vertices labeled by V1, V2. That like more corresponds to like, you know, thinking of subdividing polytopes and scissors networks. Maybe he wanted V1 plus V2 on the bottom, and then 4 or 5 pink dots.
I think I'm good. It just doesn't have to be a straight line. What used to be. I'm fine. Thanks. It's a rational homology. Yeah. So.
To me, the confusion is I keep thinking this is the projected picture versus the other picture. So I guess there's a difference between the projective picture and dealing with the definition. Is that right?
I'm not sure I understand.
So you took subspaces that were neither zero nor the whole thing. So that's the same as specifying things at one lower dimension in the projected picture, right? Because a one-dimensional subspace is a point in projective space. And so when you draw them here, you draw, you know, the one-dimensional subspaces as, or maybe I'm mistaking it. It appears this picture is projective.
Yeah.
And so if that were true, then V1 plus V2 would lie on the edge between V1 and V2. So I'm slightly...
The planes are also
And so the
planes are
plane
the
is
planes.
the line, the entire line. So it's,
Yeah, I know. I've drawn those kinds of pictures. This is sort of different. Every subspace is a vertex, right?
Oh, I
It
see,
is
it's the
represent
barycentric
flags.
subdivision.
It's a much more combinatorial thing.
Okay.
The one thing that I think might help is to put brackets around the vectors as well, not just this.
I see.
Yeah.
The two-dimensional subspace
Is a point.
yeah.
Yeah. And the edge is a flag. It's a containment relation.
I see. Oh, maybe I now understand the confusion. Yes, this is a picture in the tensor and not the partial basis complex. Yeah. Very good. Oh yeah, great. So we were going to check that the proof of the Church Farb Putman conjecture, check vanishing of the top degree homology groups of these SLZ groups in the top degree using fifth generation by integral apartment classes. Okay. All right. So, okay, so want to show that this group is 0 for n at least 2. And by Borel-Serre duality, this is the same as checking that the SLNZ coinvariants of the Steinberg module vanish for all n greater than or equal to 2. Okay. But this is generated as a SLNZ module by the apartment class associated to the identity matrix, associated to just the standard basis for Qn by Ash and Rudolph. And So it's easy to check that this one symbol has to in fact be 0 in coinvariance because we can negate it. So, right, okay, so observe that if we act by the matrix, this permutation matrix that swaps our first two coordinate axes, I've introduced a -1 to make sure it has positive determinant, but that's not really relevant because it's the same action on lines. Right, so the point is that if I act in such a way that I swap the first two columns of my symbol, then that's going to give me an orientation reversing map on the associated department, and so it's going to negate the fundamental class. Okay, great. And because we're working rationally, that implies that this will have to be 0 in coinvariance. Okay, great.
So along this line, if you have a congruent subgroup, for example, can you describe the top? I mean, so this one.
I think, Matt, would you like to comment on this question?
So yes, it's non-vanishing for for like a principal congruence subgroup. It is non-vanishing for any level. There is a lower bound that is, you can write down an analog of the Steinberg module for the finite field or finite ring, depending on whether or not your level is prime. And the map from Steinberg of Q to the n, there is a map from Steinberg of Q to the n to that. Essentially, you choose an integer basis and reduce mod n. And then that is going to factor through coinvariance because the congruent subgroup will act trivially on that module. And so that gives you a lower bound, this Steinberg module.
What did you prove in your thesis, Matt?
That this thing was surjective and calculated the dimension of these Steinberg modules.
It's known, like, the answer is known for p equals 3 and 5, or for level 3 and 5.
So this map, is this map an isomorphism?
Yeah, or
There's
it
an elaboration,
depends what
okay.
you mean by it. But yeah, something like this map is an ISO 5 and not an ISO.
Higher.
Yeah, and like the best lower bounds are due to Schwarmer currently for the top knowledge of congruent subgroups.
Yeah.
Thank you.
So I have 10 minutes, 7 minutes?
Yeah.
Okay, great. Maybe I can actually say one more thing then. Excellent. Yeah, so great. Okay. The first moral of this story is that this result on the first two cases of the Church Farb Putman conjecture follow from these sort of integrality results. In codimension 0 case, it's in this integrality result for the generators of the Steinberg module. And then in the codimension 1 case, it's an integrality result for the relators of the Steinberg module. And then in our work, it's integrality results, and it's the existence of nice syzygies with good integrality properties for the next term in the resolution. And so let me gesture at least in the case of n equals 2, how you might prove an integrality result like this. Okay, so proof of integral generation in a case 2. All right.
You mean I equals 2?
Pardon?
I equals 0, n equals 2.
I see.
This is like fairy graph, old stuff.
Okay.
Yeah, exactly. Okay, so, right, by definition, or by Solomon Titz, rather, I guess n equals 2 by definition, the Steinberg module is generated by these differences of lines, say of this form, and again I'm going to use this convention where I choose I choose to represent a line by choosing a generator like a primitive integer vector for a basis of that line. Okay, and so the goal is to show that if I fix such a vector AB, that I want to be able to express this difference as a linear combination of integral classes. Okay. And so we're going to do that using the Euclidean algorithm and induction. Okay. So here are the steps. So first I'm going to arbitrarily extend this to a basis of Z2 just by choosing any complementary line CG. And then, maybe I'll call this C prime E prime. And then I'll observe that the Euclidean algorithm tells me that there exists some integer q so that the absolute value of d prime minus q times b is less than the absolute value of b, Euclidean algorithm. Okay, and so,
Or b is 0.
sorry, did I write that backwards?
No, I'm saying or if b is non-zero, right?
Oh, sorry, right. Yeah, good point, sorry. So if, yeah, thank you. Okay. Great. So now I can throw away this basis vector and replace it with the vector defined to be c prime d prime minus q times ab. And this was chosen so that this pair is still a basis, but the d is strictly less than the absolute value of b.
So maybe it would be good to have different notation for subtraction of vectors and the Steinberg classes.
Oh, that's a very good point. Yeah, I'm sorry. So let me just, yeah, that's an excellent point. I'll just write this way. Yeah, thank you. Sorry. Important distinction. Yeah, sorry. So this subtraction operation was happening within the vector space. and not at the level of homology. Great. Okay, but these now, again, are formal symbols in my homology group. And, right, so the point is that we can iterate this process. We can repeat the process, apply it to the vector CD. And at each step, we are strictly decreasing the absolute value of the second coordinate. So by induction, we will eventually get to 0. Okay? So, right, to repeat. Right, until second coordinate is 0. And that will give us a formula to express this difference as a linear combination of integral classes. So we're done. And right, to Jeremy's point, Jeremy's comment, that secretly there's, I guess, some topology in what we were doing here. Right, so here's an interpretation of this procedure that we just did. If I let X be, well, the Ferry graph, so this is the graph where the vertices are primitive vectors in Z2, and I have an edge whenever I have an edge.
Peter whisper.
Oh yeah, thank you. Up to. Yeah, thank you, Peter. Everything's up to scaling by a unit. Okay, and I get an edge whenever the determinant is equal to, well, plus minus 1. Can't distinguish plus 1 and minus 1. Great. Okay, so maybe folks are familiar with this picture, but here's my Ferry graph. Here's 1, 0.
We need something in the middle.
Oh, sorry, something went wrong. Yeah, this is supposed to go down here. Yeah, artistic skills are not my forte. Here's minus 1, 1. Here's, 2, 1. Here's 1, 2, and so on and so forth. Okay, and great. So this. What's happening? The zero skeleton of this Ferry graph is precisely our Tietz building. And so this procedure of expressing AB minus 1, 0 as a linear combination of integer apartments, that procedure precisely corresponded to finding a path through this graph between AB and the vertex 1, 0. Okay, so great. So our proof or generation by integral classes is going to be equivalent to path connectivity of this graph. Okay, and our proof found a path through the graph from AB to 1, 0. Okay, and so to write this down more formally, okay. Wait, well, maybe I won't write it down more formally, but let me just say that this suggests, I guess, the more general strategy of some of the papers that I wrote on the board earlier, which is that we can prove these integrality results for these syzygies of the Steinberg module by embedding the Tietz building or something related to the Tietz building inside some complex and then proving a high connectivity result for that complex. Okay, thank you. Thank you very much.
Any questions for Jenny? Yes, please.
So if I take those results, so you said Steinberg module is generated by apartment classes and then by integral apartment classes, and then there was this presentation by Bajkowski.
Yeah.
What goes into the proofs of those things?
Oh yeah, well, great. So, I mean, a very short answer is that if you look at this new paper by Charleston, Radchenko, and Rudenko, I hope I'm pronouncing everyone's name correctly, they have quite a short proof, which is shorter, shorter than the other proofs there. And roughly speaking, I think what their short proof does is use a kind of Solomon-Titz argument to show that we can identify the Steinberg module with the following sum. Okay, so I'm looking at the Steinberg module for V. I've fixed a subspace W, and I'm going to take the sum over
Is V is a Q module, not a Z module, right?
V is a Q module. Yes, yeah, V is our vector space. That's right. So it's to identify this with the Steinberg module of V, and then from there, basically to like run induction by dimension.
This is a quasi-isomorphism. It's like a chain complex structure on the left-hand side, right? Anyway. Maybe I'm mistaken. Oh, my bad. Yeah, sorry.
Yeah, it's like an actual isomorphism.
Oh, yeah. Okay. Hey, I'm mistaking something else.
So you're saying there.
So right, so the quick proof of the Bajkowski result, which apparently is inspired by work of Milner, but like classical work of Milner on K-theory, is to verify this isomorphism, and then proceed by induction on dimension of V, and I guess that like verify by hand that you can set up an isomorphism to the vector space defined by the Bajkowski presentation. Right.
Let's thank Jim.